All right, today I will talk about induced representations. I think all of you must have seen that to understand the structure of a given group. Uh, Very often we look at the structure of its subgroups and factor groups. This is because of sometimes the given group is so huge that we don't have any control over that, so that directly we cannot do anything fruitful on that. So what we do, we look at its reasonable subgroups and factor groups over which we have some control. Since the structure of the main group is reflected in its subgroups and factor groups, so studying these subgroups and factor groups, we can get some important information about the structure of the given group. The scenario for representation is also exactly same. From representations of subgroups and factor groups, we can get representations of the main group. So let me first tell you the story for factor groups. So let G be a group, and K be a factor group of G. By a factor group, I mean it's a homomorphic image of G, and hence it is K is isomorphic to G modulo kernel of phi. So that is the reason for calling a homomorphic image of G. That's the reason for calling any homomorphic homomorphic image of G is a factor group of G. So now assume that there is a representation of K, complex representation. Let's call it rho. Then if you just compose rho and phi, that becomes a representation of G. In fact, it is easy to see that if rho is irreducible, then so is the composition. Thus, we see that from the representations of factor groups, or some representations of factor groups of G, we get representations of G itself. In fact, every one-dimensional representation of G comes in this way, because suppose we have a one-dimensional representation of G, so by definition it's a map from G to the multiplicative group of C. Then it's easy to see that this map factors through the quotient of G modulo G prime, where G prime is the commutator subgroup. So thus every one-dimensional representation of G is basically the composition of a one-dimensional representation of this and the projection map. Recall that when G is finite, then G modulo G prime is a finite abelian group. Then we by structure theorem we can decompose into cyclic subgroups, and from that we can determine all the characters of this factor group. So since we can determine all the characters of this factor group, so from that we get all the one-dimensional characters of the given group G. Okay, so this is the story for factor groups. Now let us focus our attention for subgroups. So assume that H is a subgroup of G, and you have a representation, let's say lambda of H on a complex vector space U. Assume everything finite. The question is, so given a representation of a subgroup, can we extend this representation to a representation of the whole group G in the most natural sense? That is, so can we extend this to a representation rho? Can we extend this to a representation rho of G such that for rho H, when it is restricted to U, that should coincide with the earlier one for every H in H. So given likewise the factor group representation or factor groups. So here the question is, given any representation of a subgroup, can we from there get a representation of G extending extending this in the most natural way? The question of this answer is yes, we can do it. The method for this is called induction, which is due to Frobenius. So now we will we will define what this induction of representation means. Okay. So let's start with a finite group G with a representation rho on a vector space V, and let H be a subgroup of G so that we can restrict this rho to H. Let's write that by rho H. So thus rho H is a representation of, it's a restriction of rho. So that is a rho H is a representation of H. Let W be a subspace of V, which is H invariant. So what I mean by H invariant is, for every H in H, rho H, W is W. So this is what I mean by H invariance. So once W is H invariant, then we can talk about the subrepresentation of rho H on this vector subspace W. Let us call the subrepresentation by theta. Now let's observe that for any G in G and H in H, so rho G H W is basically rho G composition rho H W. Rho H W is W, so this is simply rho G W. So this is for H and any G. So what does that show actually? What does that mean? It means for every coset, what you choose for every coset, this does not change for any element, for any representative of the coset, right? This is what it shows, because any representative X, if you fix a representative X, then any other representative will be of this form, X times H. Okay, so in view of that, now it is quite safe to define W sigma as rho X sigma, where X is any representative in sigma for every sigma in G modulo H. So thus, for any coset, we have a subspace, right? Now we can take the sum of these subspaces. I don't know whether it is direct or not, but currently we're just considering it's a sum. So from the very definition of rho sigma, this turns out to be G invariant. Okay, so that we can talk, so that it is legitimate to talk about the sub-representation of rho on this subspace, which is a representation of the group G. Okay, now let's define when we say that the sub-representation of rho H, the theta, the sub-representation of rho H induces rho. So we say that theta induces rho, or rho is induced by theta if this, so for each, so if first of all this sum is in fact becomes direct and it becomes whole of V. So if this is what we have. Okay, so thus we have defined induction of representations for sub-representations of the restriction. Okay, now we will define the induction. We define the meaning of induction for any arbitrary representation which may not be a sub-representation of the restriction. So suppose the lambda is a restriction of suppose lambda is a representation of H. Remember, now U is not necessarily a subspace of V. So in such a situation, we say that lambda induces rho if lambda induces rho if lambda is isomorphic to a subrepresentation of restriction which induces rho. Try to understand the definition. First, the induction is defined. First we define induction for subrepresentation for subrepresentations of the restriction, for a subrepresentation of the restriction. Next we define induction next we define the meaning of induction for any representation, arbitrary representation lambda, that is purely done in terms of in terms of a subrepresentation of the restriction as in the above sense. So try to understand. So first we define when rho is induced by a subrepresentation of its restriction to H, we have defined. Then we say that rho is induced by any arbitrary representation lambda if there is a subrepresentation of rho, there is a subrepresentation of the restriction which is in one hand isomorphic to lambda, and on the other hand it is inducing rho. So in simple words, if lambda is isomorphic to something, that this lambda is isomorphic to some representation, some means here some subrepresentation of the restriction. If lambda is isomorphic to something, that induces rho. Okay, so this is the definition of induction of representations. So now we shall look for examples. So the first example here is very simple, is a usual one. We consider the left regular representation of the group. The left regular representation, which we denote by R. So the basis of LG is EG, right? So that contains H in H, right? Is a subset of the basis. Okay, and if you remember that we have this relation for every EG and X, it is E of GX. So in view of that, we see that this subspace is actually H invariant. So the restriction of so the subrepresentation of rho H on this W, let us denote that by theta. So now I leave this to you to check that this subrepresentation of rho H, which we have just denoted by theta, that induces R. Okay. So the left regular representation is induced by this theta, that which is the subrepresentation of the restriction of the representation itself, the left regular representation itself on this on the subspace generated by these vectors. All right. So the next example is also of the same kind. We consider the action of G on G modulo H. This is the natural action on cosets. It is the natural action on cosets. So we consider the permutation representation corresponding with this assigned to this action. So thus it's a representation from G to GL of LG mod H. So LG mod H is basically spanned by E sigma, where sigma belongs to G mod H, and the action of rho G for any G on E sigma is EG sigma, right? So from this we can see that EH is that is the basis element corresponding to H is from this we can see that this is invariant under H for any H in H. Therefore, if we consider the one-dimensional subspace generated by EH, this becomes H invariant, and in fact the the representation of H, which is the sub-representation, which is the sub-representation of the restriction, becomes trivial. So let's denote that by theta. So basically theta is a trivial representation. So remember, so what I'm doing is we see that this is so this is H in this is H invariant, and the generating vector is fixed for every H. So therefore the restriction, therefore the sub-representation of the restriction becomes trivial. So which we denote by theta. Then I leave it to you that theta induces rho. Theta induces rho. All right. So next we shall look for next example. The third example is D2N. So remember, it is generated by two objects, R and rho. R is reflection, rho is R is rotation, rho is reflection, and they have this relation between them. Okay. So so we take H to be the subgroup generated by R, which is cyclic subgroup of Z modulo and Z. I see Z modulo and Z, and hence we know all the representations of H. So so these are just chi k's, where chi k has been defined earlier. Okay. And let's for any k, let's define the following representation of D2N. So we are going to define a two-dimensional representation of D2N. So let's enough to so it's a function. It has to be a homomorphism from G to D2N to GL of C2. Certainly we identify GL of C2 with GL2C. So to define this homomorphism, it is enough to mention and where these generators are going. So let's so we send R to e to the power 2 pi I k by n 0 0 to the power minus 2 pi I k by n. So this is the image of R, and rho maps to 0 1 1 0. So and you see that so sending R and rho to this matrices respectively, we get a representation phi k of D2N. Now I leave this to you to check that this one-dimensional representation chi k induces phi k. Okay. Next example is regarding Q8, okay, which is basically plus minus 1 plus minus I. So far these are just symbols. Don't confuse that with the complex number I. Plus minus k. So we take H to be the subgroup generated by I. Okay. So it's isomorphic to Z modulo 4Z. Isomorphic to Z modulo 4Z. So we consider the, so in order to define a representation of H, it's enough to specify where I is going, right? Because it's a generator. So we consider the following one-dimensional representation of H, which sends this symbol I to the complex number I. Remember, these twice are different. So this is a one-dimensional representation of H. And now I leave you to check that this one-dimensional representation induces a two-dimensional representation of Q8, induces a two-dimensional representation of Q8, which we have given in one of the problems in assignment 7. Let me repeat. In assignment 7, in one of the problems, we have defined a two-dimensional representation of Q8. Now I'm saying that that representation is induced by this one-dimensional representation. Okay, so well, the next thing we'll see that how induction behaves with direct sum. So that is, if rho 1 is induced by theta 1 and rho 2 is induced by theta 2, then we see that rho 1 direct sum rho 2 is induced by theta 1 direct sum theta 2. So that shows that so if we have two induced representations, then from that how to construct another induced representation. Then the next thing will show how it behaves with tensor products. So suppose rho is induced by theta and rho dash is any representation, then rho of tensor product rho dash, which is a representation of G. Sorry. So if rho is induced by rho dash theta and rho dash is any representation, okay, then we will see that this is induced by theta tensor product rho dash H. So that shows. So I leave all these verifications to you. These are just usual. These are just usual manipulation. So that shows that how induction behaves with tensor product. Next, we will finish with an important observation that says that suppose rho is induced by theta, and rho is, let the space of the representation be V, and this is W. So what we do is, and suppose W1 is a subspace of W which is H invariant. So remember, this means V is the direct sum of rho sigmas, and if once W is H invariant, it's easy to see that so that means rho H W1 is W1 always. So we can define rho 1 W1 sigma as well. Okay, so since the sum of W sigmas is direct, so is the sum of W1 sigmas, because if any combination becomes 0, then that sum can be realized as a sum of elements from here that individually forces each and every summand will be 0. So once this sum is 0, that sum is also 0. And again, from the definition, this is G invariant. So therefore it is a subspace of V, and now it is easy to see that this subrepresentation of theta on W1 induces subrepresentation of rho on this V1. So we have we take a subrepresentation of theta, and from that we take then we consider all the translations of W1, that gives me G invariant subspace of that gives me a G invariant sub. So again, let me repeat. So we start with the subrepresentation. So we have a subrepresentation of theta on W1. Then we consider all translates of W1 and then take their sum. That sum happens to be divided, and from construction that sum becomes a G invariant subspace. Therefore, the subrepresentation of rho on this subspace is induced by the subrepresentation of theta on W1. So as I said, this I just explained what happens and why happens. Now the detailed verifications, manipulations, I leave them to you. All right. So we will finish with examples now. So I will just finish with saying that in the beginning we said that yes, the question here is affirmative, right? The answer of the question is affirmative, and the method is due to induction. So in the next video we prove that given any representation lambda, there is a representation rho like which satisfies this in the obvious sense, and such a rho is unique after isomorphism. So in short, so in yeah, so the question that we have started with, we just said the answer is affirmative. In the next video we see that it indeed exists and unique. Okay, with that I will stop.